Hello, Professor Chen. Can you see me?
Hey, Professor Lin. Yeah, I can see you.
Oh, great, great, great. So today is our first lecture.
Cool.
Are you going to, hold on, are you going to invite some of your students to join this seminar series?
I sent the notes. Let me.
But it's fine.
double-
We have video recording every week. So feel
Okay.
free to share to your colleagues or friends.
Okay, all right.
Yeah, because I know the timing may be not good for your students.
Right. Right now,
Yeah.
yes. It's yeah.
7
It's
p.m. Is it?
It's 6 p.m. right
6
now.
p.m. Okay. Yeah. So sorry about the late dinner for every Monday. So we are
No.
9 a.m. in the morning.
I see.
Yeah.
Okay, so I saved all the talk title and from our side.
Yeah.
So we shuffled a little bit, but hopefully that's
No
good
issues.
enough.
Totally fine. Because most of our Taiwanese professors are quite flexible. Yeah. So
Okay.
if during the semester there's a need for exchange, there's no issue.
Okay, hopefully that's final. Hopefully, yeah.
Yeah, that's great. So over here we have close to like more than 10 students in the class.
Okay.
Many of them are my graduate students. Some are just students who decided to choose to select the course. Yeah, and I will be also sharing the videos to our center members. Yeah.
So I saw SK are here. Professor Gupta is here.
Yeah, I'm here.
Oh, hi, Professor Gupta. What's your time right now? Are you in LA?
Yeah, I am in India.
Okay, so thanks for joining. Sorry about the late dinner tonight.
No problem.
Yeah.
Okay, so our actually lecture time starts at 10 after 9 a.m. So it's like 4 minutes away.
Okay.
Yeah.
No problem.
So I'm going to use the keynote talk that I used last week in Genoa. I went to MESA conference right after the IDTC. And in MESA, I gave a keynote talk.
Great.
Yeah. So, sorry I didn't change the date. It was still the date of my keynote talk.
Wow, that's a very beautiful background. That's Italian, right?
Yeah, that's the the Genoa is a city next to do we call it ocean? So basically, it's a picture taken by the organizer from some high ground, so you can kind of see the water in the back.
I see. Yeah,
It's
that's good.
a really beautiful city.
So that's just happened last week then.
Last week, yeah, right after IDTC. So I had a really long travel for 2 weeks. Visited 2 different countries and gave 4 talks.
Wow.
That's a lot for me. Unfortunately, whenever we travel to USA or Europe, it's hard for us to take students because every person requires the travel for every person require quite some money. So if it's in Taiwan or Asia, we usually ask our students to give the talk. But for USA or Europe, it's very challenging.
Mm.
Yeah. Okay, so I think we are just 1 minute away. Let me say hello to my students. Oh, okay, good morning, everyone. Today is the first lecture for the Global Seminar Series. As I mentioned last week, we are working with the USC, Advanced Manufacturing Center. So right now on the Google Meet, you can see two professors, Professor S.K. Gupta, who is the director of the Advanced Manufacturing Center in USC, and also Professor Yong Chen. He is the also the member for the center. So they are right now at 6 p.m. So in the following weeks, we will be having this kind of international lectures in this style. So they stay late for the meeting, and we stay early for the meeting. And I hope this kind of international arrangement will be good for the students in the class and also for the international collaborations. Okay, great. Now, as I mentioned last week, I'm the first speaker. I am the director for Robotics Center in Taiwan Tech. And this center is underneath a larger center called the Intelligent Manufacturing Innovation Center. And we are working with USC. And hopefully after this global seminar, at the end of the year, we will invite Professor Gupta and Professor Chen to fly to Taiwan. And hopefully you guys can see them face to face. Now, in my today's lecture, I will be talking about human-robot collaboration with AI technology. So it was a project that we have been doing in the past few years based on the funding given by National Science and Technology Council from Taiwan. And this is a presentation I made last week. You can see from here, September 2nd, in Genoa, Italy, where I went to a conference called MESA. So MESA represents mechatronic, embedded systems, and applications. So for some of the students in the class, maybe you don't know me too much, but of course many of you know me. And for the international participants, I would like to introduce myself for a little bit. I got my PhD in Rutgers and did 2 years of postdoc in Rutgers. Then I came back to Taiwan to teach in a private university called Zhongyuan. And then I was promoted to National University, Taiwan Tech, in 2017. Okay. Maybe, Jerry, maybe you can full screen right here. Okay. Yeah. I'll try the other layout, the highlight mode. Yeah. This one. This one. Yeah, so the classroom can see a little better. Yeah. Then once I joined Taiwan Tech, I became a professor in 2021, and now I am serving in different areas. First one is a special program called IATP. It's a international program with 4-year undergraduate curriculum where we have non-Taiwanese in the program. And the other program is so-called the GDAP. It's basically the same program, but filled with Taiwanese. So in these two programs, undergraduate 4-year programs, we basically give lectures in English. So for non-Taiwanese, they can come here without learning Chinese. And for Taiwanese, they can study their undergrad in English, so later on in the future they can travel abroad with good language training. And then for the service in research, I am now the director for Robotics Center since last year. And I actually didn't start my research from robotics. My background in PhD was in optimization. And after I came back to Taiwan, I realized in Taiwan, if you want to get some funding, doing optimization is not enough. I need to apply to something else. So these are the research areas that I have been applying optimization in. And robotics, computer vision will be something that I mainly talking about for today. So some just basic achievement in the past few years, like past 10 years, I have been involved in many projects. In Taiwan, every project only provides certain amount of money. Is not a huge project. So I need to do more in order to take care of more students and support them with equipment and consumables. So last year I got an Outstanding Research Award in our school. In 2021, there's a Young Robotics Researcher Award from the Taiwan Robotics Society. Yeah, so pretty much that's a brief introduction of myself. Now, yeah, this is just especially for the MESA slide, because I was deeply involved in MESA since 2016, where I started my executive committee position, and just in the MESA conference, I want to let people know how I was working with other colleagues in this society. I'm not sure if you guys know Professor Yang Quanchen. So he's from UC Merced. I think probably our international participants would know him. I work tightly with Professor Yang Quanchen as well. So actually, this year I will be organizing a conference in Control. I invite him to come to Taiwan to give a keynote speech. And this picture was taken in 2022, where we have I organized MESA in Taiwan, and those are the international non-Taiwanese participants for the conference. So in today's talk, I would like to start with this video. I hope it's clear for our international participants. So right here in Taiwan's production line, we do have many kinds of situations like this, where a person stands next to a working station doing something, and usually the person needs to do multiple things, sometimes very complex, and those missions has to be done in a particular sequence to achieve certain goals, such as doing some inspection or assembly and so on. So the idea is maybe we can ask a robot to help the person to reduce the burden. Maybe during the whole process, the robot will deliver something or holding the object for the person, and we hope this kind of interaction can enhance the productivity or increase the efficiency of the production. Of course, in the video you can see the robots are moving pretty slow. The female student is working really slow because just for the demo. We hope this kind of concept can be very effective in the future and safe. So at that moment, maybe a robot arm can truly help. So earlier when in the video, you can see the female student, at some moment she reached out her hand just to demonstrate human's motion can be quite random for the robot. And maybe at the moment the robot was supposed to grab something from point A and move it to point B. But on the way, if a person's body part is going to collide with the whole robot arm, the goal of this project is to make sure the robot will not collide with the human arm. And the robot will move around the person automatically and then continue the mission. Just right here, of course the student intentionally blocked the way, and just to mimic this kind of situation can happen during the human-robot collaboration. So what happened was we have a 3D camera always monitoring the skeleton of the person, and those 3D points will be considered as obstacles. They are basically moving obstacles in the space. Whenever those obstacle points could be colliding with the robot during the moving trajectory in the next second, then we immediately perform some kind of optimization to find an optimal trajectory that is safer. So in my today's lecture, I would like to talk about how this was done. So from here on the right lower corner, you can see it's a project supported by NSTC. Basically, it's like the NSF of Taiwan, and you can see many different project numbers because we have been working on this project for several years. So over here, I'm focusing on path planning with obstacle avoidance, and I decided not to use sampling approaches or random search approaches. Later on I will talk about it. I try to use a gradient-based approach because my advisor was Professor Haichang Jia. His advisor is Panos Papalambos from Michigan. You know, when we are underneath Panos, we tend to use gradient-based approach because they don't really like sampling kind of method, such as a GA or random search kind of method. They would like to, if possible, try to use the gradient-based approach. That's why when we deal with this problem, I figure maybe we can use gradient-based approach as well. Okay, so in this, my partner right here, Professor Yang, who will be giving the talk next week, I think. So basically, Professor Yang is the professor who swapped with the Professor Gupta's time. So he will be giving the talk next time. He worked with me in this project as well. He was the person who was in charge of the human motion recognition. And we do have a third researcher in the project, Professor Zhang. He's from a different school. It's called the Taipei Tech. So Taiwan Tech is the #1 technical university in Taiwan. Taipei Tech is the #2. And we are the top 2 technical universities in Taiwan, and both in Taipei City. So for Professor Zhang, he is working on so-called like a guiding system based on laser. So we believe in highly customized production line. The human worker may need to deal with productions in many different ways, highly customized. There could be 100 or even more different kinds of products. So the person may need to memorize what he needs to do for a specific product. And maybe for a different product, he needs to do something else. So basically, he needs to learn 100 different ways to for that production mission. So we also use this laser system to guide the person. For example, using a laser to remind the person where will be the position for tightening a screw, or where is the position for applying a label, something like that. So back to what I'm mainly focusing on in today's talk. Basically, we are working with 6R robot arms, but we don't focus on the original CAD model, because during on the way of the robot moving trajectory, we need to be constantly checking whether the robot, the whole arm will be colliding with the obstacle. So it requires a lot of distance calculation between the obstacle and the robot arm itself. That's why we decided to simplify each link of the robot arm into a cylinder. So basically, we will be calculating shortest distance between a point, which is the obstacle, and some cylindrical models in the robot arm. So in this animation, it will show this robot arm was supposed to move from point P0 to point Pn. On the way, maybe there's an obstacle. So we will realize within a red portion of this path, there will be danger for collision. So before it really have contact, we will activate the optimization mechanism right there to find the dash curve on the top. So the robot will be moving around the obstacle like this. So the goal is to have a real-time calculation or a very short period of time of calculation in order to find this dash trajectory, so the robot can continue its mission without colliding. Okay, so of course there are already many existing methods, such as the potential field method. In my survey, I realized for most of the methods, it requires calculations of the distance between the obstacle and the robot itself. So in this kind of potential method, we may need to sample the space. We need to figure out at everywhere inside the working space, what would be the potential field? What's the vector for that potential? So that vector will help us to find how the robot can move from a starting point to a goal point. And in this demonstration, it's just 2D map. But in a real situation, it's gonna be a 3D grid. So for every grid point, it may require some kind of distance calculation. I figure that requires too much calculation at that moment. So maybe it's hard to achieve real-time obstacle avoidance. So the next method is a famous method called the Dijkstra. So Dijkstra is a flooding method starting from the starting point, and it will move like a grid by grid from the starting point and start to flood the entire space until some searching point finds the goal, then stop flooding, start searching, and from wherever we have search for, find the shortest path. So if we are doing something like this, then every time when we are doing this calculation, we still need to check, okay, if I do a slight move, how far away is the robot arm itself and from the obstacle. So still, we need a lot of distance calculation in real robot path planning applications. And in the 3D space, this kind of flooding requires a lot of sampling. So it could be also taking a lot of computational time. A better method would be A-star, where is a smarter way to explore the space. So every time when we are doing some sampling in the space, we don't truly expand toward all the direction. We decide, okay, which is a better direction for exploring. Like in the animation, you can see initially going down probably giving us a better chance to get closer to the goal. And at some point, the algorithm tells us to make a turn right. So a method like this avoids us sampling the whole space. However, along the way, it still requires a lot of sampling. So for every sample, again, point, obstacle, distance measurement could be needed. So without sampling the grid in the space, probably using this kind of way would be more effective. So we don't sample the complete grid. We just randomly put some point in the space and then try to connect them in this way. So only the neighboring points will be connected. And along this finite network, there could be a path from the starting point toward the goal point. But whenever you see a link that will be colliding with the obstacle, then you need to remove it. So if you want to figure out whether there's a link that could be colliding, that requires point obstacle calculation. So you need to remove the colliding links first, and then try to find the shortest path from this finite directed net. So there's a more advanced method, and probably right now the most famous method called the RRT. It's like a tree branching problem from the starting point. So you don't do too much sampling in the space in advance. You just do some sampling from the starting point, and little by little, whenever you see a sampling point that is hitting the obstacle, then you will remove it, and you will choose a branch point from the neighborhood of your center point, and continue to do this. This branch will expand until one day one of the branch will be close enough to the goal. Then you find a complete connection from the starting point to the end point. But for this method, you do see some other branches that were wasted, because you kind of need to explore, and if you're lucky enough, one of the branches will be close enough to the goal point. So there are advanced methods like this where you branch out from the starting point and the end point simultaneously, and then when two branches are closer to each other, then you connect them. So in this animation, you probably can see we may be able to use less branches. So less waste of the branches. Okay, so we try not to use those kind of sampling methods. We decided to do just a gradient-based approach. So in our approach, basically, if a robot is supposed to move from point A to point B, in general, this robot could be in any geometry. So it's a multi-body robot. So along the way, if there's an obstacle, if we treat an obstacle as a point with some radius, and when the robot moves to a certain moment, and we call this a first collision point. So we use the index F. So when this is happening, that means the shortest distance between the obstacle and some part of the robot arm equals to the radius of the obstacle. That means, okay, that's the position we have first collision. If there's a first collision point, that means there will be some moment that could be the last collision point, okay? So within this region, we call it robot collision region. We want to replace all the robot control within this region. However, if we start to make a change from the first point, we already have contact with the obstacle, with like a tangent contact. So we define like a head point and a tail point, head and tail. So we need to move a little bit backward, define some head points, and also from the last point, move a little bit back forward, define as the tail point. So from this head point and the tail to the tail point, we define, okay, this is so-called the obstacle avoidance region. So this is where we will be doing optimization. So the goal is, inside this region, we need to find some safer configuration of the robot arm and find more of those, finally connect them. Then we can get a red dash curve like this. Since we will be doing a lot of evaluations to check whether a searching configuration will be colliding with the obstacle. So if we use an effector-oriented method, then we need to do a lot of inverse kinematics and forward kinematics. So later on in my optimization, I will be focusing on the configuration-oriented design space, which means I will be mainly focusing on those x-axes. X represent a vector of the motor angles, like a particular robot arm position. For each joint, the motor is right at a certain angle. That by defining the motor angle and to achieve the any-vector coordinate, that's forward kinematics. But reversely, if I want to move the fingertip, basically any vector to a certain point, I need to reversely compute the motor angle. That's inverse kinematics. I don't want to keep on doing forward and inverse kinematics during the optimization, because that requires some time. So eventually, when I want to control the robot, I only control the motor angles. So if at the beginning, when I work on the optimization, I just focus on the motor angles and choose it as my design variable, then during the entire process, I don't even need to do forward kinematics and figure out where is the position of the any factor. That's why later on, I'm mainly focusing on so-called the configuration vector. Okay, so this is a original configuration of the robot. We need to find a safe configuration right here. So the idea is that there is a difference between the optimal configuration and the original configuration. We want this to be the smaller, we want this distance to be minimized, because we want the optimal configuration to be closer to the original one. So it won't be finding some configuration too far away from its original position. But when it's too close, it's dangerous. So we will define a constraint to limit its position. And stay away from the original position. So I will talk about the constraint later. Now let's talk about objective functions. So this is one thing we minimize. And also there are two more terms, basically the distance between the current configuration and its neighboring configuration. We also minimize those to generate some kind of pulling force between the neighbor and itself. So eventually those terms will help us to keep a good distance between the current point and the neighboring point. So this helps us to well distribute those intermediate points along the red curve. Okay, so we minimize all three simultaneously. That would be the objective function. And let's talk about the constraint. So I will be defining a function called danger factor. And there will be some region right in the middle of this obstacle avoidance region. So that's where we may have collision. So when the danger factor equals to some upper limit, we claim that's the allowable danger factor. When it's smaller, then it's safe. If it's larger, we think is dangerous. So we just want to make sure this danger factor is smaller than or equals to the upper limit. So how do we define this danger factor? We will be calculating the shortest distance between each cylindrical part of the body and the spherical obstacle. And when the center of the obstacle lies on the center of the cylinder, we call it 100% dangerous. And when the obstacle is like a tangent to any body part, cylindrical body part, we said, okay, it's like a 50% dangerous. So we define D as 0.5. And if it's far away, then D is close to 0. So we try to figure out, is there a mathematical expression that follows these rules and then that is being able to represent any possible relationship between the obstacle and the cylinder. At the end, we realize in different regions of the cylinder, when the center of the obstacle lies on different regions, we may need to use a different equation. So this is what we have. Basically 6 different regions, we have 6 different equations. And if you take a look at the dash curve right here, this is where when the center of the obstacle lies on the red dash point, dash curve, the danger factor equals to 0.5. That means tangent. So over here you can see along this curve right here, on this level, danger factor equals to 0.5. And when the center of the obstacle lies at the center of the cylinder, 100% dangerous. So danger factor equals to 1. And when the center of the obstacle is far away from the cylinder, then the danger factor drops to 0. So this is a model we're going to use to represent the relationship between the position of the obstacle and the position of any cylindrical part inside the robot. Okay, so this is a complete optimization formulation where we minimize the 2 distance terms subject to danger factor that has to be smaller than an allowable factor. And 0.5 represent tangent contact. So over here, D bar, we chose to be 0.4. So we kept a 0.1 safe margin between the robot and the obstacle. Over here, this is a constraint optimization. So I used Lagrangian formulation, so I can convert constraint optimization into unconstrained optimization. So many of you in the classroom, if you didn't take my optimization course, next semester you can take it. I will teach you how to do this. So over here, if you convert constraint optimization into unconstrained optimization, you can use some of the unconstrained optimization method to solve it. So over here, this is where we can convert everything into a problem without any constraint, only one objective function, and we use a method called Newton's method to solve it. So if you have never taken optimization, next semester you can take it. So I'm not going to take too much time on here. So we use Newton's method to solve it. So here's the overall process. First, you would like to move your robot from A to B. You determine many intermediate n-effector points. Basically, the robot controller tells us this. And then the robot controller can give us all the configurations along the way. And then we will be computing the danger factor, the D functions, based on all the configuration vectors along the way to figure out which region is the collision region. So if there's any collision point, then we will find, okay, which one is the first collision point, which one is the last one, and then you move a little bit backward and forward to define the head point and the tail point. Within the region, you solve the optimization that I mentioned earlier. And with those optimal points, you basically connect them by a curve fit, and you will find an optimal trajectory. So this is how the Newton's method was done. So here's an animation. From here, you can see a robot trying to move from right to left. On the way, the robot will be colliding with this red box. So with that robot motion, on the left-hand side, bottom figure, you can see how each motor rotates along the way in order to achieve this kind of motion. But during the way, we calculated so-called the danger factor of this path. You will see on the upper left figure, the danger factor will be greater than 0.5 at the middle part, right here. That's because the robot arm had collision with the red box. So within this region, that's not allowable. We cannot perform this kind of action. Otherwise, the robot arm will just crash into the red box. So we will be focusing on 3 intermediate points and then find newer configurations for these 3 points. So for the first point, we perform Newton's method. This is the initial design. After first iteration, second, and third, and the fourth, we reach convergence. So this is the optimal, based on the formulation that I just presented. Okay, this is the second initial point after gradient-based approach. First iteration, second, third, fourth, and fifth converged. So that's the second point. Third one, initially, first iteration, second, third, fourth, and converged. So from here you can see, originally we have 3 intermediate points. After Newton's method, we were able to find 3 newer points. So what we need to do next is to just connect them. And from here, from the left figure, you also see newer path for the motor angle. Okay, so originally, like this particular one, the dark path right here, this was the original motor angle change. Now the motor needs to change in this way. So overall, the danger factor was kept within 0.4. Okay, so you will be sure along the way there is no collision with the red box. And here's how the real thing looked like. We implemented in a Taiwanese brand of robot arm. It's called Highwing. Okay, so the upper video represents exact animation that I showed in the previous slide. The lower video represents a different case where the robot was set to move from top to bottom, and it realized there's a black box on the way. So optimization finds a different path. Okay, so same method. Our method is general enough. We implemented in a different brand, also a Taiwan local robotics brand, and it makes no difference for any brand of the robot. So it was able to, of course, the geometry is different, so the cylinder models will be different, and the entire calculation results will be different. But the goal is still being able to find an optimal path for any kinds of robot arm without collision. So that would be the part I would like to share. Maybe I talk a little bit about what my colleagues were working on. So Professor Yang probably will talk about this. He used the skeleton recognition with open pose or media pipe, and he mapped these skeleton points back to a 3D point cloud in order to be able to find the 3D points of those skeleton points. And for us, we use it as coordinates of moving obstacle. So in this particular video, the student's hand, one of the point near at the student's hand, it was chosen as the center of the obstacle. So over here, you can see the student's hand was moving around near the robot trajectory. And on the left-hand side, in the cyber world, we have been calculating how the robot should be moving. And you can see this red trajectory has been changing because we dynamically find an optimal path if the current path is still colliding with the obstacle. And since the student's hand is moving, so we have to be constantly checking if the current path is still colliding. If not, then start from the current one, find a newer one. So it doesn't, so that's how we said dynamic obstacle avoidance. So from here you can see, this is a real-time video, so for every optimization, it was, all the codes were written in C++, and the optimization could be done within, I think, hundreds of milliseconds. So for the robot company that we work with, they are satisfied with this because the robot arm, in those demonstrations, the robot arms were not moving super fast. So with this kind of ability to move away from the obstacle in real time, I think they are quite happy about the results. Okay, and recently we work with a fourth professor who is from computer science. He's working on generative AI. We want to see if how this concept can be integrated with the whole project. You already see the left-hand side, the human robot recognition, laser guiding. I didn't talk too much about laser guiding, and also my part, robot, obstacle avoidance. But on the right-hand side, we work with computer science professor, and right now we can just talk to the robot. We were using ChatGPT with documents. So in the document, we mention what's the mission for the robot. Whenever the human worker says this, what the robot should be doing based on what the person's request was. So this is the architecture. I will just quickly show integration. Sorry, you cannot hear the audio from this. But at the beginning, the students say, "Hey, robot, can you pick up something for me?" So we have been demonstrating different technologies in one video. So this is dynamic obstacle avoidance. And later on, when the robot grasps the object to the person will be doing something, and then at some point when the person has completed certain mission, the person will say, "Hey, robot, turn the object to the left." Oh, here you can see the laser guidance where laser is highlighting the position for the screw, so the human worker understands what he needs to do at a certain moment. So I will show you, he will say something like, "Hey robot, turn the object to the left." So ChatGPT realized what it means, and matching with the document we provided, and the robot realized, okay, it needs to turn left like this, and so on. So this is what I have, because there's only several minutes left. I think I will stop here. I will stop here. So maybe can we see if there's any comments from our international party, Professor Gupta or Professor Chen? I will stop here. Yeah. Thank you.
Great.
Thank you, guys.
I have one quick question, actually, very interesting. So the last one you showed ChatGPT,
Yeah.
you said there's something like a document based.
Yes.
So what's that mean actually? So you define what you are interested in and then send the API to ChatGPT to looking for those words, or what that actually exactly mean? I don't quite get.
Okay. So for certain product, the robot may need to do, for example, 5 different things. So we already tell the robot, okay, here are the 5 things that you need to be working on, but we don't. We will, for example, one line would be, okay, pick up something from point A to point B, and the other line would be, okay, rotate the part for the person. The other line could be doing something else. So for every specific description in the line, we not yet allow Chat AI to generate the robot motion yet. We not yet done that. We basically ask the ChatGPT to realize, okay, what the person mean right now. So when the person say, "Hey, pick up something for me," then the AI understand, okay, what the person's mean represents certain motion in the document, like a third motion. So the decision maker will tell all the neighboring systems, "Hey, right now we as a robot needs to do motion number 3 for the person. And all the system already know, okay, now we are in motion number 3, okay, laser do this, robot do this, and then all other surrounding machines do whatever that's needed for action number 3. But whatever that's needed for action number 3 was recorded, was programmed in advance. In the next step, we would like Chat AI to generate those steps by itself. But at this point, not yet completed. I hope could be understood.
Okay. So basically, you have a set of a predefined
Yeah.
operation that you send to ChatGPT, and then every time when the people speak something, you are trying to ask ChatGPT to identify which
Exactly.
motion or they are trying to do.
Exactly, because we realize when human works with robot, if you use a human's gesture or some kind of push button or whatever way to understand what a human needs, sometimes it's not always successful. Especially if we try to realize something by human gesture, that there's a risk of failure. So maybe the success rate is 95%. So there's a 5% of failure rate. So if we can use ChatGPT by talking and then recognizing the text, we found that the accuracy is higher, and the person doesn't need to push a button or do something else, just talk. Yeah.
That's cool. Thank you.
Okay, so I hope today's talk is interesting to our international participants from USA, and also interesting for the students. I think I spent too much time talking about too much details. So right now it's already the end of the course. So any students would like to ask any questions? Yeah, go ahead.
Yeah, I have one question. I just want to know how do you connect ChatGPT with Proton?
How to connect GPT with the system?
Yeah, with the
Okay, so yeah, the student asked how we integrate ChatGPT with the entire system. So basically, our computer science partner did this. They have a additional computer right there, and supposedly, if we have good internet, all of the student's speech will be recorded by the computer and then recognized by Whisper. Whisper AI converts audio to text, and those texts will be supposedly sent to internet, and then you have a database in the space, right? And whatever decision you make, you have a response back to the computer. But when you are in an environment with poor internet, then you may need to install some ChatGPT API in your local computer with limited function. But still, it's doable. I think for some of our demonstration, they are using a local API in the computer itself. So that computer does the text recognition and then understand the language, respond with certain human language. With the responses, it will mention, okay, like highlighting how he understands humans' request, and then which action the whole system will be doing. For example, like what I said, okay, let's do action number 3. Then this response will be sent to all of our neighboring systems, such as our robot system, our laser system. Okay, now we are doing action number 3. So robot perform action number 3, laser doing action number 3, something like that. So that's how we implement everything right now. And later on, like I mentioned earlier, we hope we don't need to pre-recorded the action, so-called action number 3. So maybe in the human's request, there are subjects, objects, actions. So, for example, maybe the sentence or the response ask the robot to pick up this coffee cup and move and deliver to the person. So maybe we need a camera in the space, in the environment, use a pattern recognition to realize, okay, this should be the object. So the robot arm will realize what's its coordinate, what's its optimal grasping configuration, and then do some grasping, and then figure out from there what trajectory the robot should be doing so that it can reach out to the person and realize when is the moment to release its gripper. You know, releasing is also very tricky. You don't know whether the person is already holding the cup. If not, then you could drop it. So that would be our next move. Thanks for the question. Yeah.
Professor, at the beginning of the seminar, you
Yeah.
talked about using a gradient-based approach.
Gradient-based, yes.
Instead of random search.
Yeah.
For application which require like faster response time,
Mhm.
which method would be more appropriate? Like for
Yeah.
example,
Because in many existing methods that we surveyed, we kind of worry if we really need to sample the space too many times. So we decide maybe the gradient-based approach would be fast enough. So of course, I do have some other students who are trying to implement sampling-based or random search-based approaches. They haven't compared them yet, but so far the gradient-based approach is quite fast. And also Newton's method is allowing pretty accurate gradient evaluation. So far the collaborating company is quite happy about the result. Yeah, but later on, if we found random search could be even faster, I don't limit anyone to use gradient base. Yeah, but so far we are sticking with it. Yeah. Okay, so question. Oh yeah, very good question. So if there's a scenario, if a moving object is moving too fast, and it's faster than how the obstacle avoidance calculation can take, then we will stop. So there is a safe in the programming logic. There is a safety guideline when the object is moving too fast, and then if you cannot find the optimal path within, for example, 200 milliseconds, then we don't even perform this motion. We will just stop. Yeah, of course, when something is too fast, moving toward the robot arm, then of course sometimes it's very difficult for robot to get away. Yeah, thank you for the question. Okay, great. I think our class also have some good responses for today's talk. Thanks to the class, and also thanks to Professor Gupta and Professor Chen. Really look forward to the next week's seminar series.
Great, thank you, Professor Lin.
Thank you. See you next time. Bye-bye.
Bye.
Okay, so before you go, you may need to hand in the whatever you written in the paper. Okay, so that's it for today's lecture. We will be doing this for the whole semester. Okay, thank you guys.